All right, so we're going to start looking at Module 1, which is linear and curvilinear motion kinematics. This will probably be some review for you based on subjects that you've, had, as you've moved along in the program. But it's also meant to kind of give us a good overview and kind of get us ready for the things that we're going to be working on. So first of all, let's look at our learning plan. So the learning plan here is going to kind of be the stuff that we're going to be doing here in our lecture time. So at the top here, it says attend each one of our lecture/demos for our module. The first PowerPoint I have out here is the one that we're going to be doing this evening. I'll have a part 2 once I kind of know exactly how far I get here. As I've told you in the past, I have a plan for getting through everything, but how it shakes out as far as how many things we get done or how many things we get through will always depend on how things go. I always want to make sure that I give you guys enough time to get through the information or ask as many questions as needed before I move on and I feel comfortable that you're okay. And then I have, a little bit here about the sections in our textbook that you're going to be then going over. So I try to be detailed as far as so you'll notice here that we're going to be looking at chapter 11, section 1, 2. We're going to skip over 3, and then we're going to look at 4 and 5. Okay. And then down here, it says follow along with the following examples. These are going to be the things that I'm going to be going over in class, okay? And most often, they're also going to be the things that you're going to have in your practice problems or the ones that you're responsible for, okay? And then down at the bottom here, then to finish off the learning plan, you're going to, do your practice problems, hand those in, submit those. And then also that leads to the application problems. Now, before we kind of open up here, I'm just going to go back one layer. And you're going to notice that then if you want to know exactly what practice problems we're going to be doing, they are going to be listed in the practice problems here. Again, the sample problems, the things that we're going to be going over in class. Now, something to keep in mind here that I do have is at the very top, I do want you to create an equation sheet. So I have one that I created for myself, as we kind of go through. I am not going to dictate what that looks like for you, but I want you to generate one that's going to be meaningful to you, okay? So in the past, years ago, I used to create the equation sheet and just hand it out. But I think there's really something for you to actually tangibly go through, write it out, and then add your own notes and make it your own because then it means something. So you do have to create an equation sheet then for this. It's not so much that I'm going to look that you have all the right stuff on it. It's just that you have a place that you can go back to and not have to always be flipping through the book. Okay, that kind of thing. And then the sample problems here that we're going to be doing, you'll notice that some of them have some Excel spreadsheet solutions that you're going to be exercising. So I'll talk about that during our lecture demo. At the bottom here, things to keep in mind in the practice problems. And this is going to be consistent with the stuff that we're going to do throughout the term. And if you had me before, sounds familiar too. First of all, make sure you show all your work as demonstrated in our lecture. So I'm going to be kind of going through and showing you the steps that we're going to be going through. And my expectation is you're copying them down the way that I'm doing them, okay? Because this is also the formatting and the way that I want you to write out the work. You're going to be submitting spreadsheet screen snips where applicable. So there's going to be some places that I'm going to be showing you how we can use Excel to write little calculators, or for a whole problem, how we can go through that process. And then you're going to then be adding the screenshots for those. Unless I ask you for the file, I don't find the need to do that. As long as you're getting the right answers, you know that it's programmed correctly. I don't need to see the file, okay? But I also want to be sure that you're doing your own work because Excel as a tool, you're going to not only be using now, but you're going to be using it a lot out in industry. And part of the reason that we kind of sprinkle it throughout the course is to make sure that you feel comfortable with it. So this is going to be another place that you're going to get to practice that. Make sure that all written work is neat, orderly, and readable. Okay. If I can't read it, you won't get credit. So make sure you're identifying givens and finds. Make sure that you include your units in your final answer. This is the one class that you get the exception. I am not going to ask you for all your units and all the phases of the problem. You guys have done a lot of that for me already. You know a lot of these units, and I don't want to, it's never a waste of time, but but there's sometimes a lot, to the units, and I'm just like, I'm gonna relax a little bit on that. We'll see how that goes, but in the final answer, make sure that you have it, okay? Um, Number your steps as you go along. Put a box around your final answer because then I know that you've answered whatever the question is asking. Use pencil and erase your mistakes. Please do not cross out or scribble, okay? Then it says here, upload your problems in the order that they're assigned. It's hard for me sometimes. You might not think it's a big deal, but if we go back up to the top here and you do number 1, but then you'd add number 17 next, and then you kind of, just put them in a random order, it's hard for me to go through those. It sounds really silly, but it really aids in me getting through it more efficiently. Not that I'm ever going to take points off if you don't do it. It just helps me out. We have, I think, 16 people in here, and there's a lot of work to go through, and I want to be sure to be efficient. So by doing that, that just helps me. Check your files to be sure that they're not blurry or hard to read, okay? You can upload PDFs, you can do JPEGs. Just please don't zip your files and send them to me because then I have to actually download it. If you do it in a JPEG or a PDF or there's some other formats I think that are okay. Oh, even a Word document, you can do it in there too. That way I can see it and view it on the screen and I don't have to download it and open it in another application. It just, again, saves me time in that process when we're going through. If it ends up happening here and there because you just forget, that's okay. I can deal with it, but it's just easier this way. If you do not follow the formatting and submitting instructions, you will not get credit for the practice problems. Remember, this is practice problems. This is a 0 or a 10. There's no, I don't give you a 5. I don't give you a 7. It's a 0 or a 10. It's kind of like I'm doing it for completion and making sure that the formatting looks good. Okay. So any questions about the practice problems? All right. So as we're going through, I wanted to tell you about the equation sheet because it's not officially, in the learning plan, but I'm going to ask you to submit one for me that you generate as we go through the module. Okay. So then let me go back to our learning plan. And we'll talk about application problems once we kind of get through the chapter, okay? So I'm going to pull up my PowerPoint presentation here, okay? And the PowerPoint presentation is just based on the book information. So at the beginning here, they're just kind of laying the groundwork and talking about the difference between kinematics and kinetics. Kinematics, as we recall, was just last term. If you had me, if it's been a little bit, you just want to recall that we're looking at the motion of a mechanism without regard to any forces, okay? So in kinematics, we're not worried about, what we're making it out of. We're not worried about what is the weight of something. We're not worried about, how much force do we have to push with it. We're just looking at, we learned about stroke. We learned about, like the distance that something would go, the space that something would occupy. It's really that first step in the design process. Dynamics, we're now going to take it that step further, and now we're going to be adding those forces as we go along. Not in this chapter specifically, but dynamics as a whole, or kinetics, we're adding the forces, okay? So we're kind of completing the problems, if you would, okay? So kinematics is a study of the geometric motion, and kinetics is going to be adding the forces to that motion, right? Now, in this chapter, we're going to be talking about 2 different types of motion. Rectilinear motion, and this is going to be where we're worried about position or distance, velocity, acceleration when we're going in a straight line, okay? Curvilinear is going to be those same objects, but now we're going to be along a curved path. Okay, so familiar to that is going to be like a projectile. We'll be looking at that, and I know that you've seen those things probably in physics, maybe even a little bit in math, but we'll be looking at some examples here as well. This chapter should be a review, okay, for places that you've been. So, but it's like I said, a good warm up to what we're going to be doing. Now, as we start looking at the first section here in chapter 11, 11.1a, this is rectilinear motion, looking at position, velocity, and acceleration. So again, these would have been subjects that you would have covered in depth in your physics class. So whether you're taking it concurrently with what we have going on right now, or if you've taken it previously, or if you had it, maybe in high school at some point, these are going to be, again, familiar to you. So first of all, rectilinear motion is going to be when we're interested in something that's moving along a straight line. Okay, a straight line. Now, as we look here, if we're looking at position, we usually identify it by coordinates, and that could be X and Y coordinates, or when we're just along a straight line, typically it's going to be either in the X horizontal direction or in the Y vertical direction. So if we're looking at position or distance, it's going to be one of those two. We also always identify an origin. We have to know like where we start, and if we have a point, where it's in relationship to that start or that origin. So in the case that we have here, notice that along the line on illustration or figure A at the top here, our origin is marked on the left-hand side here. And then as we move to the right, it looks like 1, 2, 3, 4, 5 units to the right here that are kind of hashtagged off. We have our point P. So point P, because it's in a horizontal direction, we would identify it as, if you would, a coordinate of X distance away from the origin. Now, we will see consistent in this particular unit, but you can also identify your own. But we are going to most often go along with the regular convention that things that are positive from an origin are going to be moving to the right or on the right-hand side here. So in the case of A, we would have that X coordinate of 5 units in a positive direction in relationship to the origin because it's on the right-hand side, okay? In contrast, on figure B, as we look at P prime, a new point, we're going to notice that it's 2 units away from our origin, but this time it's on the left-hand side. So that would be a negative distance direction from the origin because it's on the left rather than the right, okay? Now, the motion of a particle is known if that position coordinate for the particle is known for every value of time. So when we talk about motion, we're not just interested in just its coordinate, but what is happening as a function of time, right? So we're expecting if something has motion, it is moving. So if we look at, at time 1, where are we at? At a time 2, 3, 4, and successive, then, if you would, most often seconds, what is happening as that is moving? So at one instant in time, it could be, at a position of 5 units to the right. Maybe at the next second, it's going to be 6 and then 7 and 8 and so on. Or maybe it's changing direction and coming back towards the origin. So we have the ability to express the position as a function of time. So you're going to notice here that they just give an example of X is equal to, so X would be our coordinate along our line in relationship to the origin as a function of time. So you're going to notice that X is equal to, and then we have 6 times the time squared minus t cubed. So once we know what value of time we're interested in, we can insert that and then calculate what the corresponding distance X or the coordinate X would be. And then we can also then generate a graph. So the graph you're going to notice is going to be that X distance versus the time. So the X is going to be on the vertical axis and time is going to be on the horizontal axis. And then we can actually find and plot their points based on their time and their corresponding X distance, and then generate the best fit curve through those points to see what the behavior of that point is or the distance is as a function of time, okay? How many have seen things like this before? Math, physics, science, right? Yeah, actually. So again, this should be review. Now, as we look at the different positions and then also looking at how the positions change, we can then start identifying and giving relationships to how fast things are moving. So for instance, velocity. So average velocity is going to be taking an amount of distance that we covered divided by an amount of time that it took us to do that. So an average velocity, for instance, is if we're driving in a car down the highway and we cover 60 miles and it took us 1 hour. I'm trying to be easy about this, 1 hour to do that. Chances are for exactly an hour, you weren't going exactly 60 miles, right? Or 60 miles per hour. You probably were speeding up or slowing down over that hour, but it averaged out to be 60 miles per hour. I covered 60 miles in an hour. Okay. But instantaneously, I look at if you want to look at your velocity, it's anytime that you look down then during that time frame, down at your speedometer, and we're seeing how fast am I actually going right now. Maybe you're driving along and you know you're going a little bit fast, and all of a sudden you saw, a policeman along the side that was monitoring, how fast people are going. You might just look down like, oh boy, how fast am I going right now? And you can kind of see and then maybe adjust if you need to. But that's the difference between instantaneous and average velocity, which again, I believe that you guys have all talked about. So it's going to then let us know what the rate of change in the distance or the position that we have. Now here as well, we want to also understand how is the velocity changing over time. Okay, so at one instant in time, maybe when we start, we're at a zero velocity, we're not moving, but then as time goes by, now we're moving and we want to see how fast we are going. Okay, now positive and negative. When we look at positively directed velocity, again, velocity is a vector. So the magnitude we refer to as speed. That's what we call the scalar value. It's like, how much was it? Okay, it's just kind of the rate that we're moving. So when we look at 60 miles per hour, that's its speed, that's its magnitude. If we want to, if you would change that over into a vector, we need to know its direction. Okay, so its direction then, once we add direction, we can then give it a positive or negative based on the convention that we have. So if we're on, I-43 and we're going north, and if we assign north as a positive direction, it would be a positive 60 miles per hour. But if we're going in an opposite direction, south, for instance, if we identified north as being our positive direction, if we're going south, that means that we're going 60 miles an hour or negative 60 miles per hour, not because it's less than zero, but because the direction now is in an opposite direction. Okay, so understanding your convention, what's positive, what's negative is really important because that's also going to play into the values that we have. So as we look at our graph here for velocity, you're going to notice that this one starts out at zero. It goes above the zero, so it's positive values for a time until about 4 seconds. It crosses over, and now it starts going negative. Okay, and again, the negative and the positive are going to be which direction we're going in. So for instance, from our zero, as we're on the top of that graph, that means that we're going in a positive direction. As we move negative, that means that we've probably changed direction and now we're going in an opposite direction. Okay, so the positive and the negatives have to do with the direction for which we're going for velocity. And then our last one here is looking at acceleration. So instantaneous acceleration is when we're looking at how we're accelerating at any point in time. So for instance, I'm going to kind of point down here to start off with first. If we have acceleration that changes over time, we're going to see the line not be horizontal or straight. So in this case, you're going to notice that we start off at the beginning of this graph at an acceleration of 12 meters per second squared, okay? And then you're going to notice that we actually cross over to zero, and then we start going in a negative direction for our acceleration. Now, how many have had physics before? Okay, all right. So what is an example of a positive acceleration? What would we know if something was in a positive, considered a positive acceleration? What would that mean to us? Oh, darn it, it's on here. I was thinking it was on the next one. Don't read the slide. What's an example? I would be doing what? I would be pushing the gas pedal. So my motion, what's happened? So if I'm pushing my gas pedal, I am speeding up or slowing down when my acceleration is positive. I'm usually speeding up, right? Okay, my acceleration is going in the same direction as the motion. Negative then is going to be decelerating. That means that I'm probably, if I'm in a car, I'm probably pushing on the brake this time instead of on the gas pedal, and I'm slowing down. So the acceleration is going to be, if you would, in the opposite direction, hindering the forward motion, if you would, and we're going to be slowing down. We're still going forward, if you would, in the same direction, and our velocity is changing, but now instead of speeding up, we're slowing down. Okay, good, 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 good. Oh, the other thing that we want to mention here, and I'm going to kind of go back to the velocity. If we want to determine what the equation for the velocity is, we are going to take the first derivation or the first derivative of whatever the motion is in relationship to the position. So for instance, if we have, can't really highlight it, the x is equal to 6t cubed minus, I'm sorry, t squared minus k cubed. In order to find from our position how we find the velocity is we take the first derivative, okay? So then what we're going to do is we're going to take that x, and now we get the velocity to be 6t squared, I'm sorry, 12t, this is the position, and we're going to take the derivative of it. It's going to be the 12t minus 3t squared, okay? And then to get the acceleration, we're going to do one more derivative on the velocity. So now we're going to take it one more time, and then we get the velocity, or the acceleration to be 12 minus 6t. And then when we look at our acceleration for the equation of the line that's created, it's going to correspond. So what we can do in Excel is we can then program a table to create a graph for us to then be able to see exactly how the curves are changing for each one of the position to the velocity to the acceleration, which is what we're going to be doing today in some of these early examples. So here's a little concept quiz. What is true about kinematics of a particle? Okay. The velocity of a particle is always positive. That is false, right? Because we have, knowing whatever our positive direction is, we can have a negative, right? So that is not true. The next one, B, it says the velocity of a particle is equal to the slope of the position time graph. Okay, I see a lot of nodding heads saying yes. Okay, so let's just read the last two. That sounds like a good possibility. Just like any multiple choice question you have, you want to kind of see which ones seem to make sense, and I'll rule out the others. The next one, C here, it says the position of a particle is 0 if the velocity, or then the velocity must be 0 as well. If the position is 0, the velocity must be 0. I'm seeing thumbs down for this one. No, we could be actually crossing over the origin, right? And we could still be moving. So that one's definitely false. And then the last one here, if the velocity of a particle is 0, then its acceleration must be 0. No. How can something be not moving but have an accelerate? Oh, I shouldn't say it that way. How can it not have a velocity but be accelerating?
Throw a ball straight up, it's not moving at the top, it's graphed in the y direction, but it still has acceleration.
Excellent example. So Christian just said, if you throw a ball up at the very top of its trajectory, as it gets to that very highest elevation, there's still an acceleration on it. And what is that? Gravity, exactly. So that would make that last statement false. Okay, excellent. So B, for instance, is exactly the correct answer. Yes, the velocity of the particle is equal to the slope of the position time graph. Okay, so the first example that we're going to look at here is not one that you're going to be handing in for your practice problems, but I am going to be showing you an example of the spreadsheet solution so that you can kind of see how we can use Excel to solve these problems. So let me go underneath here first. The problem statement, or what we have here, the concept is on page 620 in our book. So I'm going to go underneath here. So on page 620, now I did get the loose leaf version of the book, so so you can kind of see what you would get. Let me focus here. Okay. So what it says here, it says, consider a particle moving in a straight line and assume that its position is defined by. I'm going to zoom in here a little bit further. So here is the equation for the position line. So it says that this is x is equal to 6 squared minus 3, okay? So what we can do with that equation is we could then plot as the time changes. So you're going to notice here that x is going to change each time that my time changes. And I want to create this graph over here in order to, determine what that is, okay? So if I go to Excel, okay, and I did do the, here it is, concept application. I did create a graph for this. So I'm going to go to my position tab. And you'll notice here that I have a very similar graph generated from the table. So I've got a column for my time, and all I did was identified 0 to 6, okay, as an example. And then I've got my X dimension here. And in the X dimension on the first one, I have my first cell at the top here programmed so that it coincides with the equation that we see here for the line. So what I did was, you're going to notice, I'm going to zoom in a little bit so that you can see. What I did was, as just so that we could see what this was, you'll notice that the function that's underneath our first cell here, B2, is going to be equal to 6 times A2 squared. Okay, so A2 is right here. I'm going to square that value, and then minus that time cubed. Okay, that same time A2 cubed. So once I had that there, I then simply copied it down, and then each time that it incremented to the next second, it then substituted the value for whatever the time was for the variable that we see here for the A2. And so as we go down for 1 second, you're going to notice that my X distance, or my position, is 5 units. And then for 2, it would be 16, and so on. And then what happened was I created a chart. Let me zoom out here just a little bit so we can see that at the same time, of distance versus time. So you're going to notice here that my distance is on my y-axis, and then my time is on my x-axis. Now, a couple things about this. I am going to have you guys create this type of an Excel file with, you'll notice, the different tabs at the bottom here. I'm not going to dictate exactly how all of your stuff is going to look. You need to generate a graph that has a title, that has the units and the axes labeled in each direction, and then just a little, if you would, table here of the 2 columns so that it can be graphed. I also want to, you don't have to, I shouldn't say that, you don't have to put what the actual function was that you put in there, because I'll be able to see if you got it right based on your values. Does that make sense? If you wanted to put it out here just as for your own reference, that's fine. But I just put it out here as text so that I could kind of show you what was programmed on the inside. So this is an application of the computer programming that you would have done, previous in this class. And then it's using this to generate not only the values that are going to be the position as a function of time, but also the graph then, so that we can see, visually what's happening. So that's going to be our position based on the value we have there. Now, if we go back underneath, okay, you're going to notice that the next thing that they did, because if you would, the problem really is just giving us the position, the equation for the line of the position. So now, to determine what its motion is going to look like, more specifically its velocity, we're going to take the first derivative of that position equation. So to do that, we are going to basically take dx over, or in relationship to the time. So now we're going to then take our first value here. If we have 6t squared, we multiply the 2 times 6, that's going to be 12 out front. And then we're going to subtract 1 from the power. So that's going to be 12t minus, and then this is t cubed. So we're going to take 3 times 1 and then minus 1. So it's going to be 3t squared. And this is the equation for the velocity. So now we're going to use this to calculate the velocity as a function of time. So if I go back to my Excel spreadsheet, you're going to notice that I have another tab, and this one is the velocity. So now using that equation of 12t minus 3t squared, I now have my time and I have my velocity. And in my velocity here is that function of 12 times our time. Or, yeah, just the time. This one didn't have a square in it. I was thinking, where's the square? But no, it's on the next one. Minus 3 times the time squared. Okay, so this is how we would write it out in there and then copy it down so that we can see how velocity changes after each, second. And then create a chart in order to show that behavior. Okay. And again, naming the chart as well as the axes. You don't have to get crazy with things here. I mean, if you want to make it pretty, that's fine, but I don't want anybody spending a ton of time just making sure that you have a title on your chart as well as your axes labeled appropriately with the right units. Okay. So in this case, we're working with, I think, feet. So then our next one is then looking at the acceleration. Now, the acceleration is going to be then the derivative of the velocity equation. So now we start with the 12t. The derivative of that is just going to be 12 minus 3t squared. So we're going to have 6t. So now we're going to go back and I created an extra tab for the acceleration. And then now you're going to see that we have that same thing. We've got acceleration as a function of time using that equation that we got from the derivative of the velocity. And again, title, the axes labeled with the appropriate units. And that's going to be that. Now, the other thing that I have on here is many times, and we're going to find this as a nice little tool, I have time in the front here. A lot of times we want to know, what is the time when the velocity is 0? Or what is the time when our position is going to be 0? Okay. So what ends up happening is, depending on what we're trying to find, and it's usually either position or velocity, we're going to use one of those values to determine, okay, when the velocity is 0, what is the actual time? So if we set this equal to 0, we end up having, in this case, a t squared and a t in there. Well, that we can't really solve for algebraically. Well, you can, but we got to use the quadratic form. Instead of writing that out each time, I created this little calculator down here so that I can solve for when the velocity or the distance is 0 for what the time is going to be. So as you know, with the quadratic form, we have an A, B, and a C. And then you're going to notice down here that it's going to cross over 0 in 2 places. Now, depending on the value, sometimes it can be negative, which may not make sense for the problem. So then you only deal with the one that is positive. In this case, we have a 0 when it crosses a 0, a time 0. And then we also had to have that time 4 seconds. So if we look at, in this case, when the velocity is 0, if we go to the velocity tab at the bottom here and we see the chart, indeed, it does happen when it's 4, even when we did it with the function. And we also see that crossing here as well. Okay, so I'm going to have you guys create a little spreadsheet, and we will do this in our first example, one that's very similar to this, so that you have the time with the quadratic function on it. You have a position where you can put the position equation in and then find the position in relationship to time and create the graph to go along with it. Same thing for velocity and the same thing for acceleration. Okay, so any questions on that at the moment? Okay, so let's go back underneath. I'm sorry, actually, I want to look at my PowerPoint presentation. So that was this one, determine the motion of a particle. We talked about using the function. Oh, the next part here before we look at our example. The next part here is another section in here. This is 11.1. And this is where they identify that, it's, as we just looked at, we had the position, we had the equation for the position line or the motion in relationship, the the position in relationship to time is where we started. Then we did 2 derivations to get the velocity as well as the acceleration. But sometimes, and actually more often, we might have acceleration given to us, and we want to kind of go backwards and find out what is the velocity and what is the position based on time. And in that case, because we're kind of going in the opposite direction, with our position, we did 2 derivations to get to first the velocity and then the acceleration. But if we're starting at the bottom, if you would, and we're working back to the velocity and the position, then instead we're going to be doing integrals, back from the acceleration. So we will see that in, I think, the second or the third example that we go over in just a little bit. So this is kind of like that chart that's there. So we are going to look first at sample problem 11.1, and we're going to kind of take this one a little bit slower, because what I want to do is I want to generate an Excel spreadsheet to solve problem 11.1 using that same format that we saw in the concept 11.1 to solve. Okay, so let's look at our problem statement first. And that means that we need to go to sample problem 11.1. So sample problem 11.1 is on page 623. And in this problem, this is going to mimic what we just looked at in that concept application. So it says here that the position of a particle moving along a straight line is defined by the relationship x is equal to t cubed minus 6t squared minus 15t minus 40. Okay, so how we start out this problem is we're basically going to start with our position equation here. So I'm going to kind of the top. Now, as we work these sample problems, there is going to be manual work alongside, okay? It's not just going to be, fully all the time, just an Excel spreadsheet, okay? So this is going to be sample problem 11.1. And we're given, I'm going to write down that equation for position. We're given x is equal to t cubed minus 6t squared minus 15t plus 40. Okay. Where it says x is expressed in terms of time. And what they want us to do for this problem is they want us to determine the time at which the velocity is 0. Okay. Also, the position and the distance traveled by the particle at that time. And then lastly, the acceleration of the particle at that time. I'm sorry, not lastly. And then the distance traveled between the time 4 and 6 seconds. Okay. So first things first, in order for us to even get to the time for which the velocity is 0, we need to get this in the velocity form. So we need to first take our first derivative of this position to get the equation for our velocity. So we are going to do that. So we're going to do velocity is equal to v is equal to, so the derivative of t cubed is going to be 3t squared, right? Minus the derivative of 6t squared is going to be 12t. Minus the derivative of 15t is going to be 15. And then the derivative of 40 is just nothing, right? It would be plus 0. Okay, so we would end here. Now, we know that we're going to be doing acceleration, so I'm going to do the next derivative for the acceleration just to have it, but we will come back to the velocity for part A. So let's just do acceleration right away, as long as we're here. Okay, so acceleration for this same thing is now going to be the derivative of 3t squared, which is going to be 6t minus 12. And then it would be a minus 0 for the 15, okay? So these are the 3 equations that we're going to be using to generate our tables and our charts, okay? Now, I'm going to open up my Excel spreadsheet for this particular problem. So I'm going to go to File, Open. I'm going to first go over what I have before I let you start doing it, okay? So if you wouldn't mind just following along with me for just a second. This is sample problem 11-1. Okay, so I'll just kind of first walk you through. This is similar to the application problem that we just looked at. Notice that my first tab is the time. This is where I want to determine what is the time for which the velocity is 0. So I start out on top here. I've got my position equation just written out. Now, a couple things about the position equation and then also the velocity and acceleration. There are powers here. I'm expecting you to write this in power form. Do not use the caret 3 or the caret 2, okay? So how you would write this out, for instance, is it would be x is equal to t, and just put the number 3 minus 6t2 minus 15t minus 40. See, 40. Okay. Now I'm going to reselect on that, and I need to get the 3 to be cubed, all right, rather than a 3t or t3. So I am going to highlight my 3 up in my, I don't know what it's called, whatever the insert where I put my stuff in. And then I'm going to go to the arrow down here on font, and I'm going to click on superscript. And then I'm going to hit OK. And notice that it makes the 3 a cubed rather than a T3 like I wrote it. Does that make sense to everybody? Okay, so you select it up here. Just highlight that one, and then you click the little arrow by the font, and you have to click on superscript. In Word, it's its own little thing, but in Excel, you've got to go into the font, okay? Then I'm going to do that same thing for the square. I'm going to highlight the 2 for the t squared, and I'm going to go to superscript, and now I have the t squared there. I am going to be looking for that. So don't leave it as T3 or 6T squared or 6T2. Make sure that they're cubes and squares and change those. And this right here is just identifying and like rewriting, if you would, what the equation is that you're using. And then I did the same thing for the velocity. Here's my derivation. So this is the 3T minus 12T minus 15. Now, let me go in detail here too on what I did down below, okay? So now down below, you'll notice that because the problem asked me, what is the time when the velocity is 0? It could have asked me, what is the time when the position is 0, all right? But it didn't. It asked me what the time was when the velocity was 0. So I'm going to use my velocity equation that I just got the derivation from the position, okay? And now I've got to put it in quadratic form. And you know, quadratic form means I'm going to have my square, then my non-square, and then I'm going to have my constant, my number. So that means that when I look at this, the 3 is in the spot for the A. Then the B is going to be the -12. Make sure you put the sign in. And then the C is going to be the -15. So down here, that's where I added that information. So I have the A here, the B, and the C. I can get rid of them here. I put it on the... Okay. Now, down here, this is just an intermittent number. I just kind of chose to do it this way so it would be a little bit easier to program. So what I put in here was the B squared minus 4AC. And I just did this work for that number. That is not an answer at all. It's just an intermediate, okay? But if you wanted to do it all in one cell, you certainly can do that. And then when I did my 2 values, because remember there's a plus and a minus, so here, this is going to be then the plus version, and then the second one is going to be the minus, okay? Now, you're probably like, what do you mean plus and minus? What do you mean A and the B's? Let's go back to the quadratic form. I'm kind of mad at myself that I didn't do that sooner, but I was like jumping in and doing my A's and my B's. So on my equation sheet, I have the quadratic form here, okay? So the quadratic form is x squared, just as a variable, whatever the variable might be. In our case, it's t, plus bx plus c is equal to 0. So when my velocity is 0, the variable that's in front of my x squared, or in our case, it was the t squared, is going to be my a value. The one in front of the x, or in our case, the t, is going to be the b. And the one that doesn't have a t is going to be our c, all right? And then the actual quadratic equation then, to solve for that variable, so in our case, because we're solving for time, but the generic version is x, is going to be the minus b plus or minus the square root of b squared minus 4 ac, excuse me, divided by 2a.
Class, my teacher showed us a video. Kind of like one of those earworms you can't get out of your head, you really want it to.
Right.
Every time I see that, I hear a song.
You hear it? Oh, did they? So that you could remember it?
Yeah. It's stupid.
It's stupid.
B plus and minus the square root of b squared minus 4.
Well, see, you don't forget it. You don't forget it, right? Some people do that SOHCAHTOA for like the things. Okay. All right. So I'll let you kind of get that down. So if we go back to our spreadsheet, this part right here was like underneath the radical. So that was the intermittent equation that I did. So that then when I did the programming, and that's this cell right here, when I did the programming for these two, then I just inserted from the above rather than making it longer. You don't have to do that. Again, this is your spreadsheet. Just make sure that you get the correct answers. And that's why the sample problems are here, so that when you set this up, you can double check that whatever answer you're getting, you can make sure that it matches so that you've got a good spreadsheet. Okay, so that's the first one. So this is figuring out what are the times when my V is equal to 0. This is the answer to the first part of that problem, okay? All right. Now, the next thing that you're going to add for this problem is a position tab, where you show the position as a function of time and the little graph on the side, okay? So as we see, and if we look at the book, you're going to notice that they show the X versus time. That's this first graph right here, using the function that we see right here. All right. So again, if I go back to Excel, that's going to be what I programmed into the first cell here. You don't have to show what your coding is. I'm going to put that in quotes. I just have it here so that you can see. So we're taking then, using the A2 as our time, and we're cubing it, minus 6 times A2, which is the time, squaring it, minus 15 times the time, plus 40. And then copying that all the way down, you should get 40 for your X, because that's where the graph starts, and you'll see that's consistent with the value in the book, or the chart in the book. And then it's going to cross, and it's going to go down to negative 60 at 5 seconds. And then it's going to go back up. Okay. And this again is the equation that was given to us for position. It's the first equation that identifies the motion. Okay. So again, if we go underneath here, it's that equation right there is the equation of the line for the graph. The next tab, and again, I'm not expecting you to do this all while I'm talking, because I'm going to give you time after this to do this. The next tab is going to be the velocity, okay? Now, the velocity, we're going to use that first derivation of the position in relationship to the time, okay? And this is the equation. So if we go back underneath here, here it is. When we did our velocity equation, we are going to then use the 3t squared minus 12t minus 15 as the equation for the line to calculate the velocity as a function of time. So if we go underneath here, that's what I just kind of showed there. Again, you don't have to show that, but it is the equation in here with A2 being the time, and then it's going to be calculating the velocity based on 3 times the time squared minus 12 times the time minus 15. And then copying that down, you'll see that at that 5 seconds is where your velocity is 0, which is what it told us on our first tab. Where is the time 0? It's at 5 seconds. Or where is the velocity 0? It's at 5 seconds. And that's when it's crossing. Okay. And then the last graph on here that you would create is going to be the acceleration. Okay. Now the acceleration is the second derivative or derivation of that position. And if we go underneath here, it's going to be the 6t minus 12. Okay, it's going to be the equation of that line. And that's going to be what you program in here for the acceleration. Copy it down. You're going to start with a negative 12. And at 5, it's going to be 18. And that's what it wanted to know, I believe, for that 5 seconds. Okay, and again, each one of your charts, I can't stress this enough, the format of the chart, every chart always needs a title. So you're telling me this is acceleration versus time. Acceleration is going to be on the vertical axis. So A, and in parentheses, what are the units? And then we have T, and in this case, T is in seconds. Okay. Now, once you have those all set up, okay, then there's a little bit more work to do to finish this problem. So I want to go over that again. I'm going to kind of finish this up, and then I'm going to give you time to then put the finishing details on your Excel spreadsheet, okay, kind of off camera if you would. So let's go back underneath, okay, and kind of finish up this problem. So if we look here, it was asking us in part A, the time at which the velocity is 0. We would look at our Excel spreadsheet and oopsie, I'm on the wrong one. Hold on. I'm sorry. This one here. If I go to my time tab, we had 2 times. We had a time of 5 and we had a time of -1. Well, we're starting at 0, so -1 is not going to be a value that we're going to worry about. So 5 is going to be the time when the velocity is 0. Okay. So you would just then, for question A, I go back underneath here. So this is the first work that I do. So for part A, we would say T is equal to 5 seconds. And you would just say quadratic calculator or quad calc. Okay. And then you would do a screenshot also of that calculation, if you would. You don't have to put the Excel file, but I want a screenshot showing me that that's what you used and kind of proving it. Okay. So that's A. So then B for this problem says, what is the position and the distance traveled by the particle at that time? Okay. So if we know that this time was 5 seconds, now what we need to do is we need to find its position and the distance traveled. So if we go back to the Excel spreadsheet and we go to the position tab where we created this, at the time 5, our position is -60. Okay. Our position equals -60. Or you could say X is equal to -60. Okay. So underneath here, that's answering that problem, and that's going to be feet. Okay. Now the other part, go ahead. Oh, I'll do that after. Again, I'm not expecting you to do that all right now, but I'll re-show that. So yeah, if you're still putting the spreadsheet together, just kind of watch what I'm doing here because I'm going to give you time when I'm done here. I just want to make sure that you understand kind of the process here and how we're using the Excel spreadsheet. So if I go back to my Excel spreadsheet, the other part of part B is not only where its position is, so this is its position, it's like X5 if you would, but it also wants to know what is the distance that we've traveled up until this point. So you're going to notice that on our chart here, at 0, we're starting at 40. So that means we're 40 past our origin. And then we cross over, and then we're going to be -60. So its coordinate is -60 at 5, but the distance traveled is 40 plus 60, 100 feet. Does that make sense to everybody? Okay. So distance traveled then, if I go back underneath here, distance traveled equals 100 feet total. Okay. We started at a positive position, and then we went past the origin by 60 feet. So a total distance of 100. Okay. The next part here, part C, we look, it says part C is the acceleration of that particle at that same time. So since in part A, we said that the time when velocity is 0 was 5 seconds. So our A, I'm going to say A5, so A at 5 seconds. I'm going to go back to our Excel spreadsheet, go to the acceleration tab, and at 5 seconds, it's 18 feet per second squared. And again, you would take a screenshot of each one of these so that you could see. And I suggest highlighting because that's answering the question, but you're just writing it up. Okay. So that's going to be, and again, this is from the spreadsheet. You don't have to calculate that because it's already done for us. And then our part D. Okay. So part D says they want us to find the distance traveled, not coordinate, by the particle going from T4 to T6. Okay. So if we go back underneath, we're going to go to our spreadsheet. We're going to go to the position tab. Okay. So it wants the distance traveled from 4 to 6. Okay. What we cannot do is we can't take, because you'll notice that we're switching direction here, aren't we? Okay. So if we take the distance at 4, the coordinate at 4, and the coordinate at 6, that only shows us a difference of 2, right? But actually, at 4 seconds, we're at a -52. We go down to 5, that's a difference of 8, right? And then from 5 to 6, it's another 10. So we went a total of 18. Do you see that? So distance traveled, not coordinate. So distance traveled, because we went down and back up. Don't take the difference between the two coordinates in this case. If they're going in the same direction, you can take the difference. But in this case, we're switching directions at that 5-second mark. So distance traveled here for part D equals, what did we say? 18, right? 18 feet total. Okay. And there's not really a way to like show that on the spreadsheet. Does that make sense? Okay. All right. So then, because we're creating a spreadsheet in relationship to this, basically what you want to do is show, if you would, the full screen snip of the time, which is going to be the quadratic calculator as well. This full screenshot of the position, the velocity, and the acceleration, and then highlight it if it makes sense to do so. So in this case, because, you know, those values that we were interested in were at the 5-second mark, or when velocity was 0 and such, you know, it makes sense to highlight those. Okay. But the screenshots just let me know that your numbers, if you would, are correct in the background, and your cells are programmed appropriately. So right now, before I let you kind of, you know, put the finishing touches and get that spreadsheet kind of in final form, I'm going to give you time here to do that, and I'll answer any questions that people might have. Are there any questions on this first sample problem? Because this is going to be one that you hand in, Josh. Oh, I can. Yes, I will go back to what I wrote on the sheet. Which one?
The answer for C.
For C? Oh, it's an A5. Sorry. lowercase a, so the acceleration at 5 seconds, because they wanted to know what is the acceleration when the velocity is 0. So that was at 5 seconds, as we found out. So the acceleration at 5 seconds is 18 feet per second squared. Any other questions? Virtually, is everybody doing okay? I'll just kind of pull the chat out here. Say that again. If we have a problem with an Excel spreadsheet, Willie had a really good question. He said, for our test, can we use Excel? Yes, you'll be able to use your Excel calculators. Yeah. It'll be in class, so I don't like looking over people's shoulders, but I might have to sit in the back of the room and look, I guess. I don't know. Yeah. As long as you don't have ChatGPT up. That's another thing I will say. If you're ever wondering, because I use it sometimes as a nice little like either check or help me get started. I mean, ChatGPT or there's other AI tools. If you wanted to use, like, ask it to write you out what would the code be in Excel for blah blah blah, and you might find that it does pretty well rather than you having to just like come up with it. Yes.
I've actually used it to explain to me how physics ideas work.
Explaining ideas. Yes. Yes. I think, at first ChatGPT, from a teacher's perspective, you felt like, oh, is that cheating? But I don't think it's any different than doing a Google search, honestly, as long as you check to make sure that your results are accurate and are consistent. Yeah.
Difference between using it as a tool not to work.
Right.
Versus using it as a tool to be able to do the work.
And be more efficient at it, right? Yeah. Okay. Any other questions? So what I'm going to do is I'll kind of leave this stuff up here. I'll also put my Excel spreadsheet up, and I'm going to give you some time to create it, and then we'll be back to continue on, and then we'll use it for the next examples that we have. So I'm going to pause the recording. Okay, so now we're going to look to the next sample problem, and we're going to use that spreadsheet that we created in the previous problem in places where it's asking for it. So let's look at our sample problem first. This is on page 624. I'm going to kind of try to scooch this over, and I'm going to minimize this. There we go. It says you throw up a ball vertically upward with a velocity of 10 meters per second from a window located 20 meters from the ground. Knowing that the acceleration of the ball is constant due to gravity and equal to 9.81 meters per second squared downward, determine A, the velocity V and the elevation Y of the ball above the ground at any time. Okay. Also, the highest elevation reached by the ball and the corresponding value of the time, and the time when the ball hits the ground and the corresponding velocity. And they want us to draw the velocity time and the position or the distance time curves. Okay. So first of all, what we want to do is we want to model the ball. And what it's telling us about the ball, first of all, is that it has constant acceleration. Now, if you recall, in kind of the second section that we looked at, it said a lot of times we're given as a definition of the motion, we start at the acceleration level as opposed to the distance level or the position level. So in that case, when we kind of start, if you would, at the bottom, okay, and I like to think of this, I'm gonna look at my little equation sheet that I created. If I know what my position is x, to get the velocity from that, I'm gonna do derivative, or I'm going to take the derivation of with respect to time of that x to get my velocity. So if you would, on this side, to go from position down to velocity, I'm going to take the derivative. Then to go from the velocity to get the acceleration, I'm going to do a derivative again to get the acceleration. But if I'm starting with acceleration at the bottom here, I got to do the opposite to go back up, right? So that means I'm going to integrate once to get to the velocity when I want to go from acceleration to velocity, and I'm going to integrate again to get to the position. So in this problem, we're given the definition, if you would, of the motion based on the fact that there's constant acceleration. Okay, so that means we're starting at the bottom here, and we know what that is. That's going to be gravity. Okay, so let's look first of all at what we're given before we jump into our problem. Okay, so this is going to be sample problem 11-2. Okay, and our givens. You always want to kind of, identify what you're given so that you can see kind of where you're going. So first of all, we know that we're going to be throwing up that ball with an original velocity of, so O is for original, or sometimes you might see it as I, that's what I'm used to, but this book uses O, an original velocity of 10 meters per second. And that is going up. So it is going to be in a positive direction. Okay. Now, they have a diagram here. Notice that they have the origin of everything down at ground level, and anything going up is positive, and anything going down or pointed down is going to be negative. Okay. So now in relationship to the ground, we know that the distance up to where we're throwing the ball up out of that window on that building, our Y, our distance, our position, our Y original is going to be equal to 20 meters. Okay. And it's going to be a positive value. I'm going to put the positives out front here where they should be, because again, it's above the origin. Okay. It's above the origin. Now, last thing we know about this ball is that gravity is acting on it throughout its entire path, if you would, as it goes up and then down and hits the ground. So we can say that A is equal to negative 9.81. Why do I have the negative sign out front? It's going down, right? It's directed down. So positive is an upward direction, and negative is going to be a down, right? It's always opposing, if you would, the motion when it's going up, but then it's going to be helping it as it goes down. So this is going to be our gravity constant, and then down for the negative. So that's our givens. So what we're going to find, okay, what they want us to find in part A, we want to know what V and Y are at any time. Okay. What V and I are at any, or V and Y are. So at any time, where do we want to know what the velocity is and where it's at. Part B says we want to know what the max Y is. So what's its highest elevation? Part C, they want us to identify the T and the V when it hits the ground. Okay, when that ball hits the ground. So it's going to go up, and then it's going to come back down, and it's going to go past where we threw it up, and we want to find out when and how fast is it going when it hits the ground. And then part D says it wants us to create the graphs and the tables. So we're going to do the Excel for that. And we kind of have that already set up, right? We just have to kind of put our numbers in. Okay. Now, because we weren't given an equation for the position, we have to determine that equation based on the fact that we have constant acceleration. So we know that since we're starting at the bottom, like we saw, we're going to integrate twice. We're going to go back up once for the velocity, and then a second time for the position. Okay. So step number 1 is going to be finding the velocity equation. And then we also need to find the position or the distance equation so that we can create the two charts with finding both Y and V in relationship to time. So to do that, we know that we're going to take dV over dt is going to be equal to A, which we also know is equal to a negative 9.81 meters per second squared. Now, as I told you, because we're kind of, dealing with a lot of stuff in the middle, the only thing that you want to be sure of is that your distances are all in meters, that you don't have any kilometers in there. that your times are all in seconds, okay? And that way we can kind of take out some of that extra stuff with the variables that go in there because there's enough going on with the math. So, and you guys have demonstrated time and time again that you know how to do the units. So that's what that's going to equal. So then we can rewrite this and we can solve for the velocity. So we can say dv is going to be equal to negative 9.81 meters per second squared times dt. And all I did was I rearranged this equation right here and substituted in the negative 9.81 to solve for the velocity. Okay. Now this is going to be what I take the integral of. Okay. So we are going to do the integral of dv, and we're going to start at v original is equal to 10. Remember, we're throwing up that the original velocity, we're throwing it up at 10 meters per second. Okay. And then the other limit is just going to be the velocity. It's going to be equal to, we're going to put the negative out front here, and then we're going to integrate the 9.81. Again, we're going to drop the units while we're in the problem here. And then with relationship to time. We're going to start out at a time of 0, and then we're going to go up to t for the limits. All right. Now we're going to do our values. So velocity and then 10 is equal to negative 9.81, put our brackets around there, and then t and 0, top and bottom. If you don't want to write that intermittent step, you don't have to. I just kind of do it to keep it straight for myself. Then I'm going to have v is equal, or v minus 10 is equal to negative 9.81 times t, and then it would be a minus 0. So now solving for v, we're going to take the 10 and we're going to add it on the other side. So v is going to be equal to 10 minus 9.81 t. So that's, if you would, the equation for the velocity, right? Now I'm going to do the equation right away to determine the distance, okay? And now we're going to take this equation and we're going to then integrate it in order to get the y value, okay? So I don't know if I have enough room here. I'm going to grab another piece of paper. So using that equation, so my step number 2 is now going to be finding the distance or position. I kind of use those interchangeably. Okay. So I know that velocity is equal to dv, dy, because we're vertical now, not x, dy over dt. Okay. And we know that velocity is equal to 10 minus 9.81 t from the previous step. Okay. So now I'm going to try that. Now we're going to take the integral. So it's going to be the integral of, oh, I'm sorry. I'm sorry. I'm going to rearrange first. I'm not take the integral yet. So it's going to be dy is equal to, because I want to get the y by itself, because I want to solve for that vertical distance. It's going to be equal 10 minus 9.81 t, and then times dt. Okay. Because I'm taking the dt and I'm multiplying this up. Now I'm going to do my integral. So my my original y is going to be that 20 meters again. And then I'm going to have a distance of y on this side. And then this is going to be the dy. It's equal to my t and my 0. So I'm going to start at a 0 time at the bottom, and I'm going to go to a time t, and it's going to be 10 minus 9.81 t, and then dTL. And now I'm going to integrate. So I'm going to do, again, if you don't want to write out this step, you don't have to. Is equal to 10 minus 9.81 t to the t and the 0. And then now it's going to be y minus 20 is equal to 10t minus, now remember you have to divide by 2. So it's going to be 4.905 t squared. Make sure everybody can see it. And it would be a minus 0 then. Okay. So now solving for y, I'm simply going to move the 20 to the other side. So my equation for distance then is going to be y is equal to, I'm actually going to write it in the quadratic form because I kind of know already that my y I'm going to have to do as a 0. So I'm going to put my quadratic form. So I'm going to put my x squared first. So this is going to be negative 4.9, I should say t squared first. Okay, so that's going to be my a, if you would. Plus 10t will be equal to my b. And then when I move my 20 to the other side, it becomes a positive. So that'll be my c. I'm just thinking ahead because I know where I'm going with this. Okay. So this then is my equation for my distance. Okay. Now, at this point, because it's asking me in part C, I think it was, yep, or no, part D, it wants us to create the charts for each one of those. So I'm going to go over to Excel and I'm going to do those right away since I have these equations. Okay. So on my time right here, don't worry about that one right now. Just go to your velocity and position. Okay. Your velocity and your position. And what you want to do is you want to program your velocity cell at the top here to be the V is equal to 10 minus 9.81 t. So it's this equation right here that we're going to use for the cell right here. So it's going to be equal to 10 minus 9.81 times the time, which in my case is an A4. Okay. Two should be A4. Just because that's the cell on mine. If you have it in a different spot, it's going to be different. You should get 10 for the first value of V, and then you want to copy that all the way down. Okay. And then through that, it's going to generate the chart that we see here. Okay. Now, I have something wrong here. What do I need to change on my graph? Yes, it needs to be meters per second, not feet per second. So I'm just going to double click here and this needs to be meters per second. So please make sure that your units are consistent with the problem. So you're going to have to kind of watch that as you do that. Okay, don't worry about my highlighted value down here right now. All right, just make the actual chart. So any questions on the velocity? Let me kind of put this out here. Once you have your velocity, you will be, and I put a little note on the top. You don't necessarily have to, but it's just a note to me, the velocity when the acceleration is constant. Notice that it's a straight line that has a consistent slope the entire time. There's no curves or changes. Once you have your velocity and you have the chart updated with the right units, then what you want to do is you want to go over to the position tab and you want to do that same thing for the position. So this is going to be a Y distance this time, not an X because we're vertical. So you want to change that to Y. You want to then program that first cell to be equal to this equation right here. Okay. So if I go back over here, you're going to notice that this is the equation. I did the 10t first. You don't have to put it in the same order of the variables as long as they're all there with the correct sign. Okay. And then I have to update this one as well. My units here are feet, so I have to change those to be meters. There we go. And then just make sure that it's, distance in the y direction to time. And then you should get 20 for your first value, and then you can kind of see the ones that I have here. Okay. And this is position when the acceleration is constant. So again, this would be showing the graphs as asked for in part D. So you can simply take the screenshots here. I did one for acceleration. It's not asking you. The question in the room was, do we need to do a chart for the acceleration? If you go to the acceleration, they're all 9.81, right? Because it's going to be the same value all the way down. So if you want to show it, you can, or you can take it off of this problem because it's not asking it. I just kind of had it there and I just reflected it. So yeah, I didn't use it really for anything. So yeah, no. Okay. How's everybody doing? Was everybody okay with those two charts? I don't want to rush anybody. I want to be sure that you get what you need. Okay, so once we have the charts, okay, created, and actually that's getting done with part D, and we have the equations for the two, now we can go back and kind of look at what are the things that it's asking us for again. So if I go to the problem statement, okay. So A was, what is the velocity, V, and the elevation of the ball above the ground at any time? Which the charts that we created, the V and the T for those. So if we go back to Excel, that answered that question. So if we go to velocity here, we know what the velocity is at any given time. And then it also wanted to know what the elevation Y was. So that's going to be here for our position for any given time. What is the elevation? So that's answering, if you would, the first part A. The second part said, what is the highest elevation reached by the ball and the corresponding value of the time? Now, if we look here, it's kind of unclear if 1 is actually the highest point, right? It probably isn't exactly 1. So what we need to do is we need to find what is that highest elevation. So the highest elevation, if we go back over here, is actually going to be the equation that we see, right? So, but we need to find what the time is. So how do we find the elevation? What would be when it would have the highest elevation? So for instance, when it goes up, right? I'm gonna kind of draw a curve. I'm gonna draw it on the paper here. When it goes up from our position at 20, it's gonna go up and it's gonna come back down, right? So when it's up here, do we know anything about it? The velocity is 0. So what we want to do is we want to find the time when the velocity is 0, okay? So if we go back to our Excel spreadsheet and we go back to our time right here, right? We know that we can find the value when our velocity is equal to 0. So we have to fill in here. Did I put the wrong one? No, that's a different one. So no, we want to put in the one for the velocity. This was the other one. That's why. So I want to put my velocity equation in here, and my velocity equation was where am I wrong on that? Yeah. Here's my previous. Oh, we don't need the quadratic. That's right. We don't need it. Kelly, duh. Been looking at all these different problems. So if we go back to where our velocity is equal to 0, we only have one value for t here, right? So all we have to do is set our velocity equal to 0, and we're going to solve for t in this equation. That doesn't need to be a quadratic on this one. So for part 3 here, we are going to say, okay, our velocity is equal to 10 minus 9.81 t. And we're going to set this equal to 0. So it's going to be 0 is equal to 10 minus 9.81 t. T is our only unknown variable here. So we're going to move our 10 to the other side. That's going to be negative 10 is equal to negative 9.81 t. You can make both sides positive. Divide by 9.81. So our t is going to be equal to 1.02. Is that right? 1.02 seconds. All right. So that's the time when we're at the highest elevation. Okay. But is that what it wanted to know? What is the highest elevation? Right. So now that we know what the highest elevation, the time that it takes to get to our highest elevation, we're going to take this t and we're going to plug it into the y equation, right? So let me grab another piece of paper, but we can actually do this over here. So if we go back to Excel and we go to our position, we can add a time of 1.02 seconds, right? And I am going to copy that cell that was at the top, and I'm going to paste it right there. And we should get a value then. I'm going to highlight this. This is going to be my elevation of 25.09 or 25.1 meters above the ground. Remember, in this case, we set the origin at the ground. So that means its highest elevation is going to be 25.1 meters above the ground. Okay. So you could then, for step 3 here, for part B, the highest elevation is equal to 25.1 meters. And you could say, you know, Excel, or like I said, if you wanted to use Excel here, you can label this to let me know there's your highest elevation. Does that make sense? So we took care of the velocity at any given time and the elevation. We took care of the highest elevation. Now we need to know the time when the ball hits the ground and the corresponding velocity. Okay, the time that it hits the ground and its corresponding velocity. So, okay, we're having this one here. So the time that it hits the ground, and this is going to be, see, time t when ball hits the ground. Okay, so when the ball hits the ground, it's going to be down here at 0, right? So to find that time, we go back up here. We know that the y is going to be equal to 0. We have to solve for the time, but there's some squares in here. So what are we going to use? The quadratic form, right? So we're gonna find what the time is when y is equal to 0. So I'm going to go back to my spreadsheet, go to the time tab, and here I'm going to put in quadratic form what the y is equal to. So it's negative 4.905 t squared plus 10t plus 20. And when we plug that in and we use the a is the negative 4.905, our b is the 10, and our c is the 20 based on the standard form, you should get our time that it hits the ground then at 3.28135. And then I labeled this the time when position is equal to 0 or hits the ground. Okay, most specifically. So screenshot here by that would be our number. Okay. And we need its corresponding velocity. So how are we going to find that? When we go to the velocity, right? So we know that it's going to hit the ground when it was at the 3 point. I'm sorry, I lost it. 3.28135. So if we go to the velocity here, 3.218, I guess I had 4. And you can put that as a time, and then you can copy the function that you had here down at the bottom in that corresponding cell, and you should get negative 22.2, 22.19 meters per second. Now, again, make sure that on your graph, you have the proper units on that vertical axis. Okay, did everybody get the negative 22? Okay.
What was the previous one? 5.
I got 3.2135, 3.2134.
See how you wrote the B squared plus 40 C. Yeah. It's not matching. It's not matching.
This one doesn't match. So B10, which is my B, squared minus 4 times A, B9 times,
If it's plus 4AC, wouldn't you, you have a minus?
Yeah, you have a minus.
In your formula
Yeah, you have
well,
minus
4AC. Oh,
But it's supposed to be mine.
Why do you have it as plus and?
is it plus and then the minus?
Here. So how I have that split out, I'll show you underneath. So if I go back over here, my little intermittent is just this right here underneath the radical. That's it. So it's B squared minus 4AC.
Now, where
So-
you have the number equals the equation that you put in, you have it as plus.
That's my fault then. I'm so sorry.
Yeah,
Oh, I
that-
did that one. I have the equation correct. I'm so sorry. That's my fault. I'm so sorry.
Minus.
So here, do you have the minus sign here? See, it's that little stuff.
Negative b plus square root.
No, I didn't put the negative on this one. So it's just B. So mine is B10 because that's that. And then it's not, I didn't put the square root in here at all. All I did was underneath, this is just the B squared minus 4AC. So yeah, it's just, I just broke that out. You don't have to. If you want to do the full equation in each one of the spots, you can. I just did a little intermittent and I never really updated it. Okay, we'll have to look at it after.
Oh, it's 9:05 then, 4:05. Did you take?
What?
4:05.
4.905. Because it's half the acceleration.
Did you put in the?
Oh, that's what I did. No, I did. Point.
Okay. All right. So that's sample problem 11-2. Are there any questions on that one? So again, we kind of went slower just to be sure everybody got their numbers as they went along, but you can hopefully you can kind of see how you can use these in order to, you know, work with some of your problems. And again, for this one, as Josh pointed out earlier, it wasn't asking us for the acceleration. I have it here just because it's there. You wouldn't have to. You could even just totally delete that tab for this problem if you wanted to. But the only things that you're responsible for would be the velocity and the position and answering the questions that it asks. Okay, so tonight, that is as far as I was gonna go, okay, or that we're gonna go. So if you're interested in between now and the next time that we get together, if you wanted to start working on some of the homework problems, the first couple homework problems you would be able to do based on what we did tonight, okay? And if we look at the problems that you have assigned, I'm gonna go back to Module 1 application problems. Let's look at these first problems, 1, 2, and 9. I'm pretty sure you can do all three of those if you wanted to just kind of test your knowledge, and you should have everything that you need for those. So the first problem that you have here is 11-1. It says a snowblower starts from start at the top of a double black or snowboarder, sorry, at the top of this double black diamond hill. As she rides down the slope, GPS coordinates are used to determine her displacement as a function of time. So they're giving you x is equal to 0.5 t cubed plus t squared plus 2t, where the t or the x and the t are expressed in feet and seconds, respectively. Determine the position, velocity, acceleration of the boarder when t is equal to 5 seconds. You can use the Excel spreadsheet to do this entire problem. Okay, so this is like very similar to the first one that we did with not quite as many things that they were asking. The second one here, 11-2, they're defining the motion of a particle with a position equation. And don't forget on the next line, it says plus 30, okay, where x and t are expressed in feet per second. Determine the time, position, and acceleration of the particle when the velocity is equal to 0. So that's going to be setting the velocity equal to 0 once you get that equation, and then using that time to determine what the velocity is at that, or to determine the position and the acceleration when the velocity is equal to time. Again, you can do that all on Excel, making sure that you highlight and or label the answers to that. Okay, so those first two you would be good on. The next one, number 9, we have the brakes of a car are applied, causing it to slow down at a rate of 10 feet per second squared. That's going to be a constant acceleration. Knowing that the car stops in 300 feet, determine how fast the car was traveling immediately before brakes were applied. So that would be the velocity and the time required for the car to stop. Okay. That one's going to be more like the second one that we did. You're starting with an acceleration. So now you're going to have to integrate to get the two others. And then you can use the Excel spreadsheet as needed. Now, if you don't use all of the Excel spreadsheet, each one of the tabs, you don't have to worry about doing a screenshot for me on any one of those parts. Does that make sense to everybody? So use the Excel spreadsheet. Sometimes it's going to be all of it. Sometimes it's going to be maybe little portions of it, but then you only have to do the screenshots that are helping you along the way or answering the questions. Okay. All right. So that's what I have for tonight. Now, the next time that we meet, we're going to be continuing on in chapter 11 here. But before we even move to the next section, I'm going to ask, does anybody have any questions on the homework? And if you do on any one of these problems, it'll be a good time that we can go over whatever you might need. Okay. All right. I know it was long tonight, mostly because we had our syllabus stuff that we started. So most often, I don't think I'm going to lecture this long. But tonight we did. So it's a little bit later. That's all I've got. So I am going to stop the recording.